We covered a few different ways to define line graph state schema, including type dicts, pydantic objects, or data classes. Now we're going to dive into reducers, which specify how state updates are performed on specific keys or channels in your schema. So let's go ahead and use type dict as our state schema to start. Here we go. We'll have a simple graph with one node. Cool, there we are. Invoke it. And we can see we return foo of 2, we pass foo of 1. That's because in our single node, we basically increment the value of foo by 1. Super simple example. Now let's actually think about this a little bit more. We look at what we input, we look at what we output. And you can see in the node, all we're doing is basically overwriting the value of foo with foo plus 1. Now, this is actually kind of an interesting point. By default, LineGraph doesn't actually know the preferred way to update the state. So by default, it just overwrites the value. So you can see the final state of the graph is just 2 because we've overwritten 1 with our update that's performed here. So that's just an interesting thing to note, that when you define your schema, by default, when you make updates, you're going to overwrite the prior value in this particular state key or channel. Now let's look at a simple case of branching. Start, node 1 goes to node 2, node 1 goes to node 3, they both go to end, okay? Now let's go ahead and try to invoke that, just like we saw before, and I'm going to do something interesting here. I'm going to try to catch invalid update errors if they occur. So basically you see here, invalid update error occurred at key foo, can receive only one value per step, use an annotated key to handle multiple values. Now think about this, is kind of interesting. We talked a little about steps previously. These two nodes, 2 and 3, run in parallel. So actually they're part of the same step. Now let's think about what's happening. If I go to those two nodes, what I'm doing is I'm actually updating that same foo state key in both of them. I'm trying to increment the value of foo by 1. But you can see this causes a problem. If I'm incrementing that same shared state key in both places at the same time, it's ambiguous as to which one I keep, right? So that is actually the reason we get this invalid update error. It can only receive one update per step. If you try to make simultaneous updates to the same key in the same step, it's ambiguous by default because you're overriding the value with two different nodes at the same time. Now this is where reducers come into play. Reducers give us a general way to address this problem and other problems because they allow us to specify how to perform state updates. Now all we need to do when we define our state schema, just like this, we just need to supply this annotated type to our key and include a reducer function. In this case, we use operator add function from Python's built-in operator module. This, when applied to lists, this will just perform a list concatenation. So what we can do is, we can say our state key or channel foo is a list of ints, and we're going to concatenate values to that as we proceed through our graph. So let's go ahead and try this with a single node. In this particular case, I'm just going to take whatever is in foo, and I'm going to go ahead and increment that by 1, and basically update that as a new list. And let's see what happens here. I run it. Now you can see 1, 2. I don't actually overwrite the value of 1 in this node, but rather I increment the list, or I append a new value to the list, which is 2. That's it. So because our key foo now has this reducer function, it knows how to handle state updates. In this particular case, because the state key is a list, it will basically just append values to my list. Now let's go ahead and look at an example graph with 3 different nodes and build this out. Same as before. We're going to do branching just like we saw previously. And let's go ahead and run this. There we go. No problem. So you can see now this has no issue running because in each of these nodes I'm just appending the value in that node to this foo list. Foo has a reducer function as we defined right here, which will just append values to our list foo as we proceed through the nodes. Therefore, it's no problem to go ahead and update that simultaneously in the same step. So that's how reducers are extremely useful and actually critical in cases where you have branching and need to perform state updates simultaneously in multiple nodes within one step. Now I want to show kind of an interesting exception here. What happens if I pass none to foo? I catch the error here, and you can see you can't do concatenation between list and none type, right? So you can have certain cases where the input value in this particular case is invalid, given our current reducer. Now this motivates the need. Sometimes we want actually to find custom reducers to handle particular types of updates. In this particular case, an edge case around handling null inputs, okay? So what we can do is we can just define an arbitrary function that handles safely combining multiple lists, and we can just simply use that as our reducer. I'm going to define this class custom reducer state to show the one that's using our custom reducer. Let's try this out. So if I just use my default reducer state and I do what I just did, we get our error, just like we saw before. Now let's try my custom reducer state. You see it works. So even though we pass in none, it can handle that without a problem. And in our node, we go ahead and we append 2 to our list. So again, just a very simple example of how you can use a custom reducer to handle interesting cases. In this particular instance, our graph can't by default handle null values passed in, and so we have a reducer that allows us to handle such cases. Now in Module 1, we showed a bit about using add messages to handle messages in state, and we also showed that the messages state is a useful shortcut to work with messages. It has a built-in messages key and has a built-in add messages reducer. So let me show you 2 examples that are actually equivalent. If I want to, I can always define a custom messages state in this particular case as a type dict. It has a key messages that has a list of messages and that uses the add messages reducer, okay? And I have some arbitrary keys I can add. Alternatively, I can just use the built-in messages state, which already has this messages key built in for me. Then, of course, I can add whatever keys I want. So typically, we'll use this built-in messages state for brevity, but I do just want to show that they're equivalent. You can always define a type dict with, a key called messages if you want to kind of enumerate this every time rather than using the built-in messages state. But I do want to show that these are actually equivalent. Now let's actually talk about the add messages reducer a little bit. I have an initial list of messages. I have a new message I want to add. I just call add messages, the initial list, new message, and you can see it just appends. So it's pretty nice and kind of works as expected. So in LangGraph, when you're using messages, each message will be appended with an ID, allowing you to do a few interesting things. So one is, if you supply the ID of a message and pass it to the add message reducer, it'll simply overwrite the value of the existing message with that same ID. So let's look at this right now. So there we go. We can see it doesn't just append this to the list, but actually changes the value of that human message with that same ID. So that's like one nice trick, is rewriting. Now the second one, removal, is a little bit more tricky, but also very interesting. So here's a message list. Each message has an ID. Now let's say I want to delete some number of those messages. I can actually delete messages by ID using this built-in remove message thing. Okay, so I just import that from LangChain Core. And I can iterate through my list. In this case, let's just say I want to remove all but the 2 most recent, okay? So I go ahead and run this, and you can see that I now have 2 remove message objects with IDs specified. If I run this with the add messages reducer, so I've supplied that initial messages list, with these delete messages, let's see what happens. So what's interesting is it goes ahead and it deletes the 2 messages per ID as specified here. This is actually a very nice trick for culling and managing your message history, and we'll show how this can be used in a future session.